Let me show you the substitution for that formula that I found with Excel on the end of the last video. It said it was n minus 1, which for us is 10 minus 1, s squared, but we know what s squared is because s squared is the variance, and they gave it to us. It's 377.7. Divided by sigma squared, but we said that that was 20 squared, i.e. 200. Oops, I suppose I could do it. Sorry. Now this one we have to square because we were only given the standard deviation, which was 20, so we have to square it. This I don't need to square it because that's what I actually got out of Excel. It was 377. It is the variance itself. And then when I used Excel to find it, I found that it was about 8.498. Okay? All right, so if you did that over and over and over and over and over, like I did right here, see these numbers, 8.49 and so on, okay? If you do that and take all of those numbers, 8.49, 8.06, 3.99, and so on, and you graph them, notice, right? You make this graph right here. You have now created something called a chi-square distribution. You're not graphing z's, you're not graphing t's, you're graphing these statistics, these chi-squares. And look at what you see here. Now notice a couple things, and you can kind of see it from the table when you go back to Excel and look. If you look at my Excel spreadsheet, I don't know if you can see it, maybe it's too small. Look at all these numbers. What do they all have in common? They're all positive. Why? Well, because you're working with variance and standard deviation. And variance, actually, and sample variance and sample, or population variance, excuse me. But variance is squared. If it's squared, it'll never be negative, right? So let's start with that. So part one, what do you notice about this distribution? It's always positive. Because variance is squared, it can never be negative. Right? Chi is squared. Variance is squared. Sample variance is squared. The whole thing is squared. It never is going to be negative. Another thing to notice is that it's very much right skewed. For many reasons, but one of them is because you've cut it off at the left-hand side. So it is not normal. Right? It's got a big right tail. All right, that's the chi-square distribution as a setup. That's how it works. Now, you've seen the chi-square statistic. You know it has n minus 1 degrees of freedom. Much like the t-distribution, there's actually lots of chi-square distributions, infinitely many, one would say. And they are affected by their degrees of freedom, which means they're affected by the sample size. So I have a whole bunch here drawn. Here's one where there were 2 degrees of freedom. Here's one where there were 5 degrees of freedom. Here's one where there were 10 degrees of freedom, 15 and 30 and so on. Okay. Now notice what happens over time. What happens over time is that the curve gets more and more, well, normal. The purple one's not quite normal, but it looks a lot closer to it. It's still got a bit of right tail. But this pink one or this orange one, they're very much right skewed. Notice none of them ever are 0. That's just nature of the beast. All right, so we've learned some lessons, so let's write them up. What are some things to note? Okay, first of all, these distributions are not symmetric. That's a big deal. This is the first distribution you've worked with that was not symmetric. Can't be. They're right skewed. It's a classic example of not being symmetric. Oopsie. Let me copy that text box. Okay, next. The shape of the distribution depends on degrees of freedom, just like the t-distribution. The larger degrees of freedom, the better in general. But, oh, and that's what I wrote here. As the number of degrees of freedom increases, what happens? Well, look, this purple curve is almost normal, right? It becomes closer to normal. The larger your sample sizes, the more your degrees of freedom. And then, last but not least, the values are non-negative, i.e. they're greater than the magic number 0. They have to be. All right? Okay, because the chi-squared... Oh, we're done here. I got to stop here and we'll see you next time.